Welcome to Thought Frontier.
All right, buckle up, everyone, because today we're diving into some pretty mind-blowing science.
Yeah, get ready for it.
You guys sent us a ton of research and articles about gravity, gravitational waves, and that never-ending quest to understand dark matter.
Well, that's exactly where we're headed today. We're going to be talking about cutting-edge physics and astronomy.
The stuff that's literally changing how we see the universe.
Exactly.
And get this, scientists might have actually found gravity without mass.
I know, right? It's almost like finding a cake without any flour or sugar. How does that even work?
It's a real head-scratcher, isn't it?
Yeah.
But a physicist at UAH, Dr. Liu, he thinks he might have found a solution.
Yeah, he's been working with these gravitational field equations, and he's come up with a solution that allows for gravitational force, but without any detectable mass.
Okay, so for like a century now, we've been saying that these weird discrepancies we see in gravitational forces, especially in galaxies, is because of this mysterious thing called dark matter, right?
Right, exactly. Dark matter, which, by the way, we've never actually directly observed.
It's like this invisible glue holding the universe together.
Yeah. But Dr. Liu's work, it's basically saying, hold on a minute, what if there's another explanation?
What if we've been looking in the wrong place this whole time?
Could be.
So that's what's so exciting about this research. It's challenging the status quo.
Absolutely.
Speaking of changing how we understand things, we have to talk about Professor Matthew Bales.
Oh, yeah. He won the 2024 Prime Minister's Prize for Science for his groundbreaking work with gravitational waves.
Which, just to remind everybody, are those ripples in space-time that Einstein predicted way back when.
Yeah, and it's amazing to think that we can now actually detect these ripples. It's like
we've gained a whole new sense.
Yeah. Professor Bales has this really amazing analogy he uses to explain gravitational waves.
What's that?
Imagine two neutron stars, each with a mass 500,000 times that of Earth, orbiting each other in this warped space-time.
So you've got these incredibly dense objects zipping around each other, creating these ripples.
Exactly.
It's like a cosmic dance.
It is. And for 100 years, we never detected a single one.
It was all theoretical.
Right, just like in those thought experiments from undergraduate physics. But now, thanks to projects like LIGO,
the Laser Interferometer Gravitational Wave Observatory.
Exactly, we're detecting them
regularly.
About once a week, right?
About once a week. It's incredible.
I mean, that's got to be like going from dial-up internet to super fast broadband. It's a total game changer.
And it's only going to get better.
Really?
Yeah, advanced LIGO, it's expected to boost its range even further in the next decade.
Yes.
We might be seeing 5 or 6 times more detections.
So imagine hundreds or even thousands of gravitational wave detections every year.
Yeah, mind-boggling, the amount of data.
But what exactly can we learn from all this cosmic chatter?
So much. Gravitational waves, they can help us accurately measure distances across the universe. We can figure out how old the universe is.
And they're not affected by all that dust and distortion that messes with our telescopes. So it's like getting a super clear view of the cosmos.
Professor Bales compares it to listening to the universe pop like popcorn.
Each pop, a black hole merger.
Wow, but wait a minute. I thought black holes were, well, black. How are we hearing them merge?
It's the incredible energy of their collision. It creates these powerful gravitational waves that, we can detect. Remember, these waves travel through space-time itself, so they bypass all those usual obstacles.
It's like having a secret back channel to the universe's most dramatic events.
Yeah.
I love it. So this information, it can help us tackle some of the biggest mysteries in cosmology, right?
Oh, absolutely. Things like the nature of dark matter, for example.
Yeah, because even though Professor Bales is a pioneer in this field, he hasn't quite cracked the code of dark matter just yet, has he?
Not yet, but he's working on it. His work with the Square Kilometre Array, it aims to detect gravitational waves from supermassive black holes.
Which could give us some serious clues about the universe's composition, really.
Exactly. And it's amazing how it all ties together. You've got these incredibly dense objects like neutron stars and black holes, warping space-time, sending out these ripples. And those ripples, they hold secrets about the stuff that makes up the universe.
Including that mysterious dark matter. It's like a cosmic detective story.
It really is. And speaking of mysteries, we can't forget about dark energy.
Oh, yes. Dark energy. The force that's making the universe expand faster and faster. It's like dark matter is pulling things together and dark energy is pushing them apart. It's a cosmic tug of war.
Yeah, it's wild. But how do we even study something as elusive as dark energy?
That's a good question. It's invisible.
Well, this is where it gets really interesting. Scientists have discovered an incredibly rare gravitational lens system.
Ooh, tell me more. What is it?
It's called the carousel lens.
A cosmic carousel. Now, I am intrigued.
So picture this. A cluster of galaxies about 5 billion light years away. It acts like this giant magnifying glass, right? Bending and distorting the light from 7 even more distant galaxies behind it.
So it's like those funhouse mirrors at the carnival, but on a cosmic scale.
Exactly. And get this, the alignment is so precise that we're seeing multiple distorted images of these background galaxies. It's a spectacle. Scientists have described it as 8 needles precisely lined up inside a haystack.
Wow. And here's where it gets even cooler, right?
No, yeah. One of these background galaxies, it's displaying an Einstein cross, the largest one ever discovered.
Hold on, an Einstein cross. What is that?
It's this rare configuration where the light from a distant galaxy is bent by a gravitational lens, and it forms 4 images around the lensing object. A perfect visual confirmation of Einstein's theory of general relativity.
So it's like the universe is putting on a light show just for us, but it's got to be more than just pretty pictures, right?
Oh, absolutely. The carousel lens, it's a goldmine of information. Because the way light bends, it depends on the mass of the lens, which is mostly dark matter.
Yeah.
So by analyzing the shape and position of these multiple images, scientists can map out where the dark matter is, even though we can't see it directly.
That's brilliant. So the carousel lens, it's not just a visual treat. It's a powerful tool for studying this invisible universe.
It's like using the universe as a giant lab to study dark matter and dark energy.
Exactly. And speaking of pushing boundaries, Professor Bales's work with the SKA is particularly exciting because
It aims to detect gravitational waves from those supermassive black holes.
oh, wow.
Which could offer even more clues about what the universe is actually made of.
Including dark matter.
Including dark matter, yeah.
I mean, it's just incredible to think we can use these ripples in space-time to probe the invisible universe.
I know, right?
But, okay, let's rewind for a second.
Sure.
Earlier, you mentioned we're detecting these gravitational waves about once a week.
Yeah,
How do scientists even know where to look?
that's a great question. It's not always easy.
Right.
It's kind of like trying to listen for a faint whisper in a crowded room.
Yeah, good luck with that.
It can be tough to pinpoint where it's coming from.
So how do they do it?
Well, there are a few ways. Sometimes other telescopes, they'll detect a bright flash of light or a burst of gamma rays that happens at the same time as a gravitational wave signal.
Ah, so it's like a cosmic treasure hunt.
Exactly. One clue leads to the next.
You follow the trail.
But sometimes it's more challenging.
I bet.
Professor Bales mentioned these mysterious signals called fast radio bursts, FRBs.
FRBs, okay.
Yeah, they're incredibly powerful bursts of radio waves.
Coming from
Deep space.
deep space, wow.
And some scientists think they could be linked to events that also produce those gravitational waves.
So it's like another piece of the puzzle.
Exactly.
We're putting it all together.
And right now, there's this kind of a friendly competition going on between Australia and Canada.
Oh, really?
Yeah, to study these FRBs.
Oh, that's interesting.
Australia's leading the charge in pinpointing them, figuring out which galaxy they came from,
Okay.
while Canada is winning the race in finding the largest number of them.
So it's like a cosmic race, huh?
It is. It is.
But what's the end goal here? What are we hoping to learn from these FRBs?
Well, the goal is to use them to understand what's called the electron content of the universe.
The electron content.
Yeah, basically how much normal matter is out there, which helps us understand, the overall composition of the universe.
Right. So we're getting a better picture of what the universe is made of.
Exactly, which is essential for understanding the really big picture stuff, like
Dark matter and dark energy.
yeah, it always comes back to those big mysteries, doesn't it?
It does. It seems like every new discovery just leads to more questions.
It does. It does.
But that's what makes this so exciting, right?
It is. It is. Keeps us going.
It does. All right, let's talk about the future of this field.
Okay.
Professor Bales mentioned these amazing third-generation detectors.
Yeah.
What are those all about?
So that's projects like the Einstein Telescope and Cosmic Explorer.
Yeah.
Think of them like the next generation of these gravitational wave observatories.
Yeah.
Designed to be, get this, 10 times more sensitive.
10 times.
Yeah, than the current ones.
Wow. What will that enable us to see? Or hear, I guess I should say.
It'll open up a whole new world of possibilities.
Like what?
We'll be able to study the evolution of things like black holes and neutron stars going way back, like back to the beginning of the star formation era. We're talking billions of years into the past.
We're talking about the early universe.
Yeah.
It's amazing.
We might even be able to observe events that we just can't see right now, like the mergers of these intermediate mass black holes,
What?
which fall somewhere between those smaller stellar mass black holes and the supermassive ones at the centers of galaxies.
Right.
So there's this whole range of sizes.
It's mind-blowing to think we could witness events that happen, shortly after the Big Bang.
I know.
But I have to ask,
Yeah.
how do you even begin to build a detector that sensitive?
Yeah.
What are the challenges?
Well, these third-generation detectors, they're really pushing the boundaries of engineering and technology. I mean, we're talking about building these massive instruments with arms that are up to 40 kilometers long.
40 kilometers.
That's longer than a marathon.
Wow.
And that leads to some really interesting challenges, for example.
Yeah.
Professor Bales talked about how the Earth's curvature
Okay.
and even the bending of the Earth's crust over such long distances can actually cause problems.
I can imagine.
For building these detectors, so it's not just about having enough space, it's about accounting for the Earth's own movements and distortions.
So it's like you need to build these detectors on a planet that's perfectly still.
Well, not quite, but minimizing those distortions is key. And then there's the whole issue of noise.
Yes.
Remember, these detectors are incredibly sensitive, so any little vibration or disturbance can throw off the measurements.
Makes sense.
Professor Bales called it Newtonian noise, which is caused by things like density fluctuations in the Earth's crust and even changes in atmospheric pressure.
Wow. So it's like trying to hear a pin drop in the middle of a rock concert.
Yeah, pretty much.
That's a good analogy.
So yeah, overcoming these challenges, it's essential if we want to reach the sensitivity we need to detect those incredibly faint gravitational waves.
There's like this constant battle against noise and interference.
In a sense, yes.
But scientists are always up for a good challenge, right?
They are. They're developing all kinds of innovative techniques to minimize those disturbances.
Like what?
Well, for instance, the Einstein telescope, they're planning to build it underground.
To shield it.
Yeah, to shield it from some of those surface level disturbances.
Clever.
And they're developing really sophisticated noise cancellation methods to filter out those unwanted signals.
It's amazing how much ingenuity goes into this.
Yeah.
But even with all those challenges, the future of gravitational wave astronomy sounds incredibly bright.
Oh, it absolutely is. We're really on the cusp of a new era of discovery, one that will undoubtedly rewrite how we understand the universe.
As we're talking about all this, I'm reminded of that cosmic carousel we discussed earlier.
Yeah.
It's almost like this visual representation of the power of these gravitational forces.
It is the carousel lens. It's a fantastic example of how gravity can actually warp and distort space-time, creating these amazing visual effects.
And it's a reminder that Einstein's theory of general relativity isn't just some abstract concept.
Right.
It has real, observable effects.
It does.
That we can witness across these vast cosmic distances.
Exactly.
And the fact that we keep finding these amazing examples, like that giant Einstein cross
I know.
in the carousel lens, it shows just how much there still is to discover.
Oh, absolutely.
It's like the universe is constantly revealing these new secrets, inviting us to delve deeper into its mysteries.
It is. It is.
And as we delve deeper, we gain these new insights into the forces that govern the cosmos,
Yeah.
including that elusive dark matter and dark energy.
Yep. All connected.
So it seems like every path leads back to those big unknowns.
Yeah, that's true.
But hey, that's what keeps us exploring, right?
Exactly. It keeps us going.
Absolutely. And speaking of exploration, let's shift gears for a second
Okay.
and talk about Dr. Liu's groundbreaking theory
All right.
on gravity without mass.
Yeah.
Remember, this idea challenges our fundamental understanding of gravity. I mean, it's pretty mind-blowing to think that everything we thought we knew about gravity could be turned upside down.
Right.
What would be the implications if Dr. Liu's theory actually turns out to be correct?
Well, for one thing, it would mean that we've been attributing certain gravitational effects to dark matter
Right.
when there might be a totally different explanation.
So it's like we've been looking for our missing keys under the streetlight.
Exactly.
But maybe they were in that dark alley the whole time.
Yeah. And Dr. Liu's theory is like shining a flashlight into that alley, you know?
It's urging us to look in a new direction.
Exactly.
So this doesn't necessarily mean that dark matter doesn't exist.
Right.
But it means we need to be open to other explanations.
Right. Absolutely. We have to keep an open mind and consider all the possibilities.
And that's what's so great about science. It's this constant process of questioning and testing and refining our understanding.
It is. It's always evolving.
And Dr. Liu's theory, It's a perfect example of that. Pushing the boundaries, making us rethink our assumptions.
Absolutely. It's exciting stuff.
You know, it's amazing to think how much our understanding of the universe has changed, even in just the last few years.
I know, right?
And with projects like the SKA and these third-generation gravitational wave detectors coming online,
Yeah.
I mean, who knows what we're going to discover next?
The next few decades are going to be mind-blowing, I think.
It really makes you wonder what's just around the corner.
Yeah.
What kind of textbook rewriting discoveries are waiting for us?
I know, it's so exciting. And you know what's even more exciting?
What's that?
It's not just professional scientists making these discoveries.
Oh, you're talking about citizen science?
Exactly. Citizen science is huge. With projects like Galaxy Zoo, where anyone can help classify galaxies, or Einstein at Home, which uses your computer's idle time to search for gravitational waves, you don't need a PhD to contribute to cutting-edge research.
That's so cool. It's like everyone can be a part of this grand quest to understand the universe.
Exactly. Science belongs to everyone.
It really does.
The universe is full of mysteries.
And it's up to all of us to explore and uncover them.
Absolutely.
So to all our listeners out there, keep that sense of wonder alive.
Yeah.
Never stop asking questions.
Keep exploring.
And who knows, maybe you'll be the one to make the next groundbreaking discovery.
Maybe you'll change everything.
That's a wrap on this deep dive. Thanks for joining us.
And until next time, keep looking up at the stars.